All right, today we're going to discuss integration by part. If you notice it, at the end of 1A, you did fundamental theory of calculus part 1, fundamental theory of calculus part 2, and then you went ahead to do U substitution. So solving integrals by using the method of U substitution. Now, this is a special kind of integration technique, and this applies where your U substitution cannot help you, all right? So it doesn't work. If you try to apply the power rule of integration, also doesn't work. So in this case, you're going to get two functions. Most of the time it will be two functions, where one of the function is very easy to integrate, the other function is very easy to differentiate. Once you see that combination, you know you're dealing with integration by part, all right? It's not always the case that the two functions will be very obvious. Sometimes it might just be one single function, but I'm going to show you all the tricks, all right, how you're going to solve those kind of problems. So let me just activate my stylus, all right, it's activated. So the first thing I'm going to explain here is, where do we come about with this constant integration by part, all right? So we assume that f and g, these are differentiable functions, all right? So remember, when you apply your product rule of differentiation, all you need to do is to keep one function constant, you differentiate the other function, plus now you keep the other function constant and you differentiate the first function, all right? That is just me applying the product rule. Now, if I apply integrals, if I apply integral there and I apply integral on this side, notice what happened. The integral of a derivative of the product of a function is just the product of that function, all right? So integration cancels out with differentiation. That's why you end up with f of x, g of x. On this side, I just need to split the integral sign, all right? So that's how you got this point and this step here, all right? Guys, please mute your mics. All right, now all we need to do is to rearrange this. So rearrange it means I just need to take this one piece here to the other side. So I need to take this piece to the other side. And once I do that, I have my formula for integration by part, right? So let's see how it works. All right, there you go. Let me just clear these annotations. All right, so there you go. By rearranging, you end up with something that looks like this. Now you can either write the formula of integration by part like this, but if you choose to use the u and the u prime, v prime, and v substitution, I'm also happy with that. All right, so I'm very pleased if you choose to use those. And how do we apply those? I'm just going to show you now quickly. You see here, you let u to be f of x, therefore u prime is just f prime of x. You let v prime to be g prime of x, and v will just the integral of a derivative of a function is just the function. All right, very important, the two notation. You can use what you see in this first box here. Integral uv prime equals to uv minus integral v u prime. You can use that, or you can say integral of u dv equals to uv minus integral of v du. Any of this works. If you choose to use the initial functions, which is integral f of x g prime of x dx equals to f of x and g of x minus integral g of x prime. If you use this, it's perfect. All right, so any of these three, you will get full marks. All right, as long as you use them correctly. Now the trick is, how do we choose between u and v prime? Very important. You need to know a v and you need to know a dv. The trick is that u has to be a function that becomes simpler when differentiated. I've been saying this for so many years, and students seem to think they understand when they don't actually understand. When I say a function gets simpler when differentiated, it means that, for example, if I differentiate x squared, which is a parabola, what do I get? I get a linear function. So it becomes 2x, it becomes linear. You see the power is dropping, all right? So that is the meaning of getting simpler. So it's something you move from higher powers to lower parts, all right? And if you differentiate stuff like x, you just get a constant of 1, all right? So it gets simpler. Now, dv is a function that is readily integrated. So it can be readily integrated. Please never choose your dv to be a function that you can integrate, all right? So if you choose dv to be something you can integrate, already it's wrong, all right? So if you choose u, you differentiate u, and it doesn't get any simpler. Let's say it gets even complicated after differentiating, therefore your u is wrong, all right? If you choose dv and you can integrate that, automatically it is still wrong, all right? So the goal of integration by parts is to obtain a simpler integral than the one we started with. How does this work? I give you a very straightforward integral, and you identify this is integration by parts, because most of the time you're going to see the product of two functions, and then you go ahead, you choose your u, you choose your dv. After performing the derivatives, you write out the formula of integration by parts, but you realize that it gets way complicated, all right? So you end up with an integral that is even complicated than the one you started with. Then all you need to do is to go back to your initial substitution and swap the values for u and dv. All right, most of the time that is going to work. If you choose u and dv in the wrong order, things will get way complicated. Just go back, swap them over, and things are going to work. Now I choose to add these things here. I'm just gonna explain it quickly. All right. So let me see if I can get my annotation again. All right. Now, if you can choose your u successfully, then automatically the other function is just dv, all right? And what concept is there to help us to choose the correct u? Is this thing here, it's called Liete, all right? How does Liete work? So Liete means you're going to choose u in this order, all right? You look at the integral, you will see if you can identify a log function. When I say logarithm, it can be natural log as well. So a log or a ln, all right? They all logarithmic function. If you don't see any of those, then try inverse function. Is there an inverse function? Sine inverse, cos inverse, or tan inverse? Or if you don't see any inverse function, then you keep going. You find algebraic function. Okay, this is a tricky one. Algebraic function is a very large, is of a very large scale, all right? Why do I say that? There's so many possibilities. It could be a linear function. It could be a polynomial. So x raised to some power, those are algebraic, all right? And sometimes it can be root function as well, all right? X to the power half is just a root function. It's still algebraic, all right? So if you don't see any of those, then you go to trig function. Everyone knows trig, obviously. It's your sine, your cos, your tan, your cosec, and so on. It's just trig function. Then the last one, exponential function. Please don't mix up with these two, because most people tend to confuse these two, all right? Algebraic function, exponential function, they're different. Exponential function is a number raised to the power x. It's defined as a raised to the power of x. So it's a number raised to the power x. For example, e to the power x, all right? That's a basic one that everyone knows. That's exponential, all right? Once you have x now raised to some power, that is algebraic, it's not exponential. Please don't mix those two. All right, now let's see. Let's look at the first example. I'm sure most of you, you've looked at this already, but let's just go through it step by step. Look at this first one, straightforward and easy. You have integral of x sine x dx. Obviously, if you follow Liete, Liete says we check for a log function. There's no log function. Inverse function, there's no inverse function. Algebraic, yes, we have an x there. That x is a linear function, all right? So it's algebraic. Therefore, your u has to be x. Once your u is x, therefore dv or v prime is just the next function, which is sine x, all right? And if you apply the concept, so u prime, if you differentiate, is just 1. If you integrate, remember when you say dv or v prime, you have to integrate to get v. So if I integrate sine x, I get minus cos x. All right. Many times when I ask a question like this, people tend to ignore this negative sign in front of the cos x. When you integrate sine x, you get negative cos x. Very, very important. Now, if you apply your formula for integration by parts, it's just uv minus integral v du. So it's just minus x cos x minus integral of minus cosine x, and that is very straightforward, all right? Minus minus is plus, the integral of cos x is just sine x. Very important, because this is an indefinite integral. What's the meaning of indefinite? Indefinite means there's no bound, all right? It means I need to see a plus c, it's a must. So if I give you an indefinite integral, I need to see plus c. If I give you a definite integral, it means it's a bounded integral. Then you're going to apply fundamental theorem of calculus part 2, which is you equate your integral using the upper bound minus the integral on the lower bound. All right. Having said that, we just keep going. Okay, now example 2 is a little bit of a tricky one. The reason why I say it's a tricky one, because it's just one function, it's ln of x. Now you guys are, you're going to say, but wait a second, you said it works only when you have an f of x and a g of x, all right? Remember I mentioned that it can be a single function. If you see integral ln of x dx, obviously you need to think of integration by parts. Why? Because we can take our v prime or our dv to be the invisible one that we can see there, all right? There's a one there. So your u, so if you go to Leate, the very first thing there is logarithmic function. You have a ln x, it's natural log, therefore your u has to be ln x. You ask yourself, what is dv? dv is just 1, all right? It's 1 times dx, all right? And if you differentiate ln x is 1 over x, and if you integrate constant, which is 1, you just get x. And the next step is very straightforward and easy. Everyone can solve that. Now, example 3, what am I testing example 3? Example 3 is a situation where you apply integration by part, but it doesn't necessarily take you to a straightforward answer, right? It still gives you an integral that requires integration by part, right? I'll just get my pencil again. So notice it. Obviously, we can see that there's a t squared here, all right? So this is algebraic, so obviously your u has to be t squared. If you follow Leate, so the first thing that you hit there is the algebraic. Remember, e to the power t is the very last thing, is the exponential function, right? So your u has to be t squared, obviously. If you differentiate, you have 2t. If you integrate e to the power t, you just get e to the power t. But look at what happened. You apply integration by part, but you end up with something that looks like this. There's a t e to the power t dt, which still requires you to integrate again. Now you ask yourself, this is a product of two functions again. How do I do this? It's another integration by parts. So you need to, again, choose a new u and a new dv, and then you apply integration by parts the second time. That's how you're going to get to the final answer, all right? So please go practice. Now, if you notice in my example, I have something like C1, and I said C1 is minus 2C. Guys, a constant is a constant. You can, if you have 2 times a constant, just give it a new name. If you leave it as C, it's still fine. I'll still give you the mark. But if you choose to move from C to a new constant K, then that proves to me that you understand in depth, all right? But I won't mark you down because you didn't say C1, you said maybe C something. No, a constant is a constant. 2 times a constant is a constant, all right? I don't want to see you say 2C, just say C, it's fine. All right, having said that, let's see what the next one is. Now, example 4, this is where things get even more tricky, all right? For example 4, the idea here is, if you use Leate, you're going to notice that your u has to be sine x, all right? It's a trig function since e to the power x exponential. That is perfectly fine. What I'm trying to show you is that there are 2 ways of doing this. The 2 ways is, the first thing is, if you choose your u to be e to the power x, or you choose u to be sine of x, it works. Why? Because both functions is easy to differentiate, and none of them get any simpler when you differentiate, all right? That's a trick there. And both functions, they're also easy to integrate, all right? So because none of them get simpler when you differentiate, you can choose them in any order, all right? But the trick there is, you need to apply integration by part twice. Why? because when you apply the second time, you end up with something that looks like what you started with, all right? So if you notice there, after applying it the first time, you end up with integral e to the power x times cos x dx. If you apply integration by parts again, you notice it, you end up with something that looks like this, e to the power x sine x, which looks like what I asked you in the beginning. So all you need to do is to group all the integrals that look the same. So you have integral of e to the power sine x dx equals to this whole thing here minus integral of e to the power sine x. Just take this other integral to the left-hand side. You end up with two of those integrals, all right? So you group them. So as a little reminder, whenever you see a combination of trig and an exponential function, you have to apply integration by part at least twice, all right? And the idea here is to group like integrals and then just make that integral the subject. If you notice here, I had a C, and because I'm dividing all two by 2, I end up with a C1, which is just equals to C over 2. Like I said, you don't need to tell me that C1 is C over 2. You can just call it a K, or you can leave it T as C. It's fine. I understand. All right. I'm not very strict about that. Now we introduce what we call definite integrals. I've already mentioned what definite integral is. It's now you have bounds. Definite integral means you have bounds, integral from A to B. How does it work? Again, we apply the formula for integration by part, but notice it, for each of these p's here, you need to apply your fundamental of calculus part 2. So you're going to say the integral. So the bound is going to be from A to B, and this integral itself is going to be from A to B. All right. So let's see how it works with this one example. You have a tan inverse function. You see it's one function. What do? You think of the other function, which is the invincible one. All right. So your u is the inverse function. If you differentiate tan inverse, you just have 1 over 1 plus x squared. As a reminder, you must know how to differentiate sine inverse, cos inverse, and tan inverse. You can have any of those, all right? Unlike inverse functions. And then v prime is 1. If you integrate 1, you just get x. And if you do that, notice it, you end up with this integral from 0 to 1 x over 1 plus x squared. And there you can do a u substitution. Guys, be careful. When you do integration by part, and you notice that you need to do it again, like the previous example that we saw, you more than welcome to still use u prime, v prime, and v, all right? If you do integration by part many times, just keep using u and v prime or u and dv. But however, if you have to switch from integration by parts to a u substitution, be careful. This is where there's a catch there. You can say u equals to 1 plus x squared. You can do a u substitution. You started by telling me that u is tan inverse of x when you're doing by parts. Now you do a u substitution. You're telling me u now changes to 1 plus x squared. Don't do that. Just use a different variable when you're doing u substitution. All right. Because although if you say let u be this, in your head you know what you're doing, but the person marking you is going to ask himself, okay, what is u actually? Because initially you told me that u is tan inverse, and now u has a different value. All right. When you switch from integration by part to u substitution, just change the variable to maybe a t or a w or a k. All right. And if you do that, obviously make sure you always do your change of bounds. Integral 1 over u is Lin absolute value, very important. Apply fundamental of calculus part 2. There you go. Straightforward and easy. Now, these homework exercises, please, you need to do them. Use the textbook that I mentioned, the 8th edition. Do these examples. Ask the